Let's look at Gram-Schmidt orthogonalization and QR factorization. We can use the Gram-Schmidt orthogonalization process to produce an orthogonal or orthonormal basis for any non-zero subspace of Rn. For example, let x1 be 1, 1, 1, 1, x2 equals 0, 1, 1, 1, x3 equals 0, 0, 1, 1, and let W equal the span of x1, x2, x3. The set x1, x2, x3 is linearly independent, so it's a basis for W. Construct an orthogonal basis for W. Recall that this is a basis in which the vectors are orthogonal to each other, and you can see that these vectors are not orthogonal to each other. So here's the Gram-Schmidt orthogonalization process. We'll go over these steps one by one. This process generates a vector v2 in W that is orthogonal to v1, and then a vector v3 in W that's orthogonal to both v1 and v2, etc. So step 1, let v1 equal x1 and w1 be the span of x1. So in this case, v1 is just 1, 1, 1, 1, and w1 again is the span of x1. Step 2, let v2 equal x2 minus x2 dot v1 over the length of v1 squared times v1. In other words, we'd say that x2 is the projection of x2 onto w1, the subspace w1. Okay, so here's x2. Here's x2 dot v1. Here's the length of v1 squared. Here's v1. Do the math, and we end up with 0, 1, 1, 1 minus 3/4, 1, 1, 1, 1. In other words, it's negative 3/4, 1/4, 1/4, 1/4. Note that v2 is a linear combination of x1 and x2, so it's going to be in W. Also, the two vectors v1 and v2 are orthogonal. You can check that. So we're on track. Step 2 prime, multiply v2 by a constant to simplify later calculations. It doesn't matter how long v2 is, so we don't need to have these weird fractions in it. Instead, let's multiply by 4 so that we end up with negative 3, 1, 1, 1. Points in the same direction. It has a different length, but at least we get rid of those nasty fractions. Step 3, let v3 equal x3 minus x3 dot v1 all over length of v1 squared times v1 minus x3 dot v2 over length of v2 squared times v2. In other words, we're going to have x3 minus x3 dot v1 over the length of v1 squared times v1 minus x3 dot v2 over the length of v2 squared times v2. Do the math, and we end up with this. Simplify the fractions. 2/4 is a half, 2/12 is a sixth. And then when we multiply it out, we get this. So then when we add them together, we end up with 0, negative 2/3, 1/3, 1/3. So that's our v3. Step 3 prime, multiply v3 by a constant to simplify later calculations. So again, we don't need to deal with these ugly fractions. We can just multiply that by 3, and v3 would be 0, negative 2, 1, 1. So this is our set, v1, v2, v3. This is an orthogonal basis of our subspace. We can check our answer. Based on how we constructed v3, we know that v3 is a linear combination of v1, v2, and x3, so it's in W. Also, the two vectors v1 and v2 are orthogonal to v3. You can check that out by just making sure that the dot product is 0. So this set is an orthogonal basis for W. Construct an orthonormal basis, u1, u2, u3 for W. Why isn't the above basis an orthonormal basis? The vectors are not unit vectors. They're not vectors of length 1. And the difference between an orthogonal and an orthonormal basis is that in an orthonormal basis, the vectors have length 1. Well, all you got to do is take these vectors and divide them by their length. Okay, and then you get a set u1, u2, u3 that's an orthonormal basis. So do the math. The length of the first vector is going to be root 4. Second is root 12. Third is root 6. So this is what we end up with. Okay, 1, 1, 1, 1 over 2, negative 3, 1, 1, 1 over root 12, and 0, negative 2, 1, 1 over root 6. We can use the Gram-Schmidt orthogonalization to obtain the QR factorization, or QR decomposition of a matrix. For very large matrices, this can speed computation or prevent rounding errors. If A is an m by n matrix with linearly independent columns, then A can be factored as QR, where Q is an m by n matrix whose columns form an orthonormal basis for the column space of A, and R is an n by n, invertible upper triangular matrix with positive entries along the diagonal. That is the essence of QR factorization or QR decomposition. So again, this is what I restated this, so the same thing. Okay, so QR factorization for A. So notice that these are the columns that we saw earlier. So first we construct an orthonormal basis U1, U2, U3 for W. In other words, the column space of A. So in this case, the column space of A is the space W we were looking at earlier, because these columns, they were the ones that, W was the span of those three columns in the previous problem. So we construct an orthonormal basis for the column space of A. We've already done this. This is an orthonormal basis for the column space of A, in other words, W. So Q, again, remember what Q is going to be? Q's columns form an orthonormal basis for the column space of A. So in this case, we've got this, and this, and this. So Q's columns form an orthonormal basis for A. Let's find R. Since A equals QR, you might think that we could multiply both sides by Q inverse to get R by itself, but that won't necessarily work. Q might not be a square matrix. Only square matrices have inverses. Instead, do this. Turns out that R equals Q transpose times A. Why is that? Well, Q transpose A is the same thing as QR, so we have Q transpose times QR. But Q transpose times Q is going to be the identity matrix, and so we end up with IR, in other words, just plain R. Now, why is Q transpose Q equal to I? Because the columns of Q are orthonormal, and the dot product of a column with itself is 1, because it has length 1, and the dot product of a column with a different column is 0, because the columns are orthogonal to each other, so the dot product's all going to be 0. Okay, so we get R equals Q transpose times A. We know what Q transpose is. You just interchange the rows and the columns. Okay, this is our original matrix A. Multiply those together, and you end up with R. Notice that R is upper triangular and has just positive entries along the diagonal. So we can check our answer. QR, when you multiply them together, turns out to be A. That's great. Hate to tell you this after going through those tedious details, but Mathematica and Wolfram Alpha can do this. Wolfram Alpha is the free online version of Mathematica. If you enter this command, orthogonalize those vectors, again, with Mathematica, you have to be really careful about your punctuation and capitalization. Wolfram Alpha is more forgiving. If you orthogonalize this set of vectors, you end up with what we had. And if you enter QR decomposition of this set of vectors, you get the following. Okay, you get A, Q, and R. A, of course, we already had. Q and R we didn't have. Now this Q and R may not look like the Q and R that we had, but they're really equivalent if you do the math.